the International Panel on Climate Change has made 4 kinds of predictions called scenarios. They're called these RPC 2.6 to 8.5. And it's just how much extra forcing due to anthropogenic change. And most of the curves I'm going to look at are either the green or the blue one. The green means if we stop putting carbon in basically right now. Okay? It's a dream. The blue is if we kept doing what we're doing now. And my personal opinion is I always look at the blue because that looks like what we're doing. But the only real change that's happened I've seen is we've converted from coal to methane. Okay, so here's some of the predictions. Global average surface temperature. So here is continue as we are now.
John, there is a pointer if you use the center button there, you can actually.
Oh, great, thanks. Okay, so here, if we continue to emit carbon the way we are now. Here is if we stopped emitting. Pretty much. It's not exactly that, but I don't see that happening. So I always look at this one. And we'll get to some global pictures in a second. Sea ice extent. Okay, I should put the timing. 1950 to 2100. Okay, so at 2100, continuing the way we are now, we'll get, it looks like 3.5 Celsius degrees, and I roughly double that to get Fahrenheit. It's not exact, but 4 degrees Celsius is roughly 8 degrees Fahrenheit. Sea ice extent. So if we continue as we are now, roughly at 2050, okay, 35 years from now, the summer will be ice-free in the Arctic. So this is something our children will definitely are going to see.
Northwest Passage.
Yeah.
That's always great.
The Canadian Navy and the U.S. Navy take this very seriously, and they're changing their plans and their strategies, what kind of ships they're constructing. This is real to them. Global surface pH. Okay, right now they show it at 8.15, and business as usual, it will go down to 7.8 roughly. So that could dissolve shells of shelled animals. Lots of shelled animals, though, actively build their shells, so they don't just passively respond to this. So it doesn't mean everything with a shell loses its shell and dies. It means more, they have to put more effort into building their shell. Here is the temperature across the globe, which is much more interesting to me than the average, because some places don't change much. So as we look right here on the tropics, they're changing about 2 degrees Celsius by 2100, assuming we just keep emitting carbon. But if you look up here in the top of the northern hemisphere, you're getting 10 degrees Celsius, or roughly 20 degrees Fahrenheit. That's a large change. And that's qualitative change in the environment. If you look at precipitation, remember warm air can hold more water, and it's more energetic, so that air can get transported across the continents. So the anticipation is there will be an increase in rainfall, but again, it's localized. It's some places like Mexico are drier, and they're already dry in this region, so they get drier. Up here in the Arctic, it gets much, much wetter, so warmer and wetter. So, like, if you look at this from the point of view of farming, you can say that you have these very large continents in the northern hemisphere. They actually get wider as you go north. It's going to get warmer and wetter, so crop production could actually go up. Crop production will probably go up even without adaptation. In other words, you don't move and grow different things. But if people adapted, famine is not one of the things from global warming. You could have increased food production.
I guess doesn't more CO2 mean more?
Right, and plus you have the CO2 fertilization
plant activity.
All this is controversial, and of course, don't hear people talking about that, but I was involved in plumbing for a long time, so that's the first thing I think about. You know, the world roughly has anywhere from a 90 to 120-day food supply. That's it. There's not 7 years of food out there. And so it's interesting, you know, most famines are because the food isn't where the hungry people are. It's not, it has nothing to do with production.
On that center chart, is the blue and the green right there at the equator, is that like El Nino or anything like that?
This is more like, you're getting the most solar intensity here, so you have the most evaporation.
Okay.
And that's current, that also happens now, it's just going to increase under these models.
Okay.
Like if you go to Colombia, you're mostly going to see clouds.
Yeah.
There's some very high mountains there that you won't see the whole time you're there. Oh, and the last thing, sea ice extent, which I got in the last slide. In the summer, there isn't going to be sea ice. Like right now, this is actually military. Submarines go and hide under there. That's where everybody's submarines are hiding. Okay, radiative forcing due to aerosols. Now, Mike went into this in some degree. What's interesting is, will we, like right now, the intention is to reduce aerosols, and that will cause warming, the red. But some people want to do geoengineering, and the most commonly heard geoengineering proposal is to intentionally increase aerosols, particularly something like sulfur dioxide, which would make sulfate particles and that indirect cloud reflection. So that's one of the proposals, one I find personally scary. But
So the upper chart is basically saying China's not going to clean up
right.
because it doesn't heat up at all.
Well, what they're saying
It's
is,
already hot.
what they're saying is,
The upper chart is the 2.6, is the aggressive.
but they are saying that China's going to clean up, and as it cleans up, it gets hotter because they're cleaning up the pollution, and pollution is keeping it cooler. Do you understand?
Yeah.
And it's actually a significant effect. Like here's the degrees. It could be a couple degrees Celsius. So we're actually cleaning up our atmosphere of pollutants. The non-carbon dioxide part can cause warming too. And so some people want to deliberately increase those pollutants. But back to that previous slide, if you did something like put a bunch of aerosols and reduce the sunlight, you would also reduce the precipitation, and you could easily have famine, in my opinion. Famine in different places, and then you're going to have some very angry people.
Yeah, just to point out that, if you recall the chart on the one I showed, that was almost all blue at the lower right-hand corner.
Right.
And now it's almost all red. And so it changes from a cooling effect to a warming effect.
Okay, global sea level. Sea level is two things. One, of course, it's going to impact people who live at sea level. But the other thing, that is the very best temperature gauge that we have for the Earth. Most of the heat at the surface of the Earth is in the ocean because it's very high heat capacity. The atmosphere has, or the ocean has a heat capacity, the entire ocean roughly 1,000 times what the entire atmosphere is. So that's where most of the heat is. And so if you wanted to know whether the surface of the Earth is warming, you'd want to know, is the ocean warming? And we don't have probes throughout the depth of the ocean or the surface. We just have ships following the shipping lines. But sea level integrates the entire ocean. It's adding up the effects from the bottom all the way to the top. And so if we can measure that, then we'll be able to see the temperature increase. And most of it, like Mike was saying, is because as ocean heats up, it expands, just like a mercury thermometer. So sea level is just like a giant thermometer. And here we have the business as usual. We're going to get roughly 3/4 of a meter by 2100. And even if we stop emitting, we still get half a meter. This shows the different components for the sea level increase. So if we look at the 8.5, is from Antarctic. Green is from Greenland melting. But this red, thermal expansion, that's the largest component. Water's just expanding as heats, because even though it doesn't expand much, it's 2 miles deep, roughly, the ocean. It's very deep. Okay, mean surface temperature beyond 2100. So this one's going up to 2300. And this, if you look at the details in the projection, what they're saying is it's business as usual. Somewhere out here we either run out of carbon or we finally stop burning it. So it's not flattening out because the effects are being stopped. It's just we finally don't burn anymore. But here you can see by 2300 that would be over 7 degrees Celsius, close to 8 degrees Celsius. So the Arctic might be 30 degrees Fahrenheit. And things like that have happened in the past, so which I'm going to talk about briefly.
So what does our rise due to if they're not using carbon?
Well, they're using carbon up till here,
Yeah.
and then there's it continues to heat because the atmosphere is still full of carbon. It comes up to a new equilibrium.
I think there's just a plateauing of the amount of carbon. It's not so much that it's not being released, it's just plateauing.
Okay, climate targets and stabilization. So here's one you see in the talked about a lot, but even if you look in the journal, some people are saying that this is was a bad idea, ever bring this up because it's impossible. And so it will disillusion people. They'll, if you ask people to do things that are impossible, then they just give up altogether. That's the psychology of it. And so, like, one of the things I argue about a lot in, say, nature climate change is that this was a mistake to even bring this up. And the other thing that you'll hear mentioned is not the parts per million carbon dioxide in the atmosphere, but how many tons of carbon dioxide have we put up there since the beginning? Cumulative total anthropogenic carbon dioxide emissions in petagrams. And so Mike up here told me that 1 petagram is 1 gigaton, is another way of saying it. And so you'll hear, if you read the newspaper, some people will say that we need to limit the total emissions to, say, 1,000 petagrams. I don't know how useful that is. But another thing that's kind of interesting from the psychology of it is some people, particularly in other countries, will say, we should feel guilty because we emitted most of these petagrams, and they assign guilt to each country depending on how much petagrams they emitted in the past. Meaning they should give money to the other people.
Let me point out this one, the fourth bullet down, dealing with this 2 degrees C thing. So it's interesting that to reach the 2 degrees C with a probability of 33% or 50% or 66, the emissions from 1870 must be held to 900 petagrams for the 33, 820 for the 50% probability of meeting it, and 790 for the 66, realizing that 500 has already been emitted. So,
It's not going to happen. Okay, I want to put up the past again for 2 reasons: to look at climate change in the context of our past, and also to discuss some experimental tests. So this curve shows the temperature anomaly. In other words, the difference between the present temperature, what we have now, they're calling 0, and the anomaly. Was it warmer or was it cooler? And then this is the time scale. It covers the Phanerozoic. It's a logarithmic scale, so this part is the last 10,000 years. Here's the last 1,000,000 years. Here is the last 60-some million years, the Cenozoic. And then here's the rest of the Phanerozoic. It goes from the Cambrian to the Cretaceous. So I think the first thing you should see is that the temperature is constantly changing, right? Sometimes by very large amounts. So here we have the ice sheets expanding and contracting. Here we have the Eocene maximum. And what I want to point out on this is that right now, one of the best tests of those climate models is they can reproduce this curve. They can show the geographical distribution of the ice sheets. They even get that ice-free corridor going through Alaska and Canada to connect Beringia to Wyoming. That comes out of a physics model. So that's one of the tests they do. They'll put in the shape of the continents, the tectonics, and just run that model and see if they can get these things. See if they can get this. And it works very well, surprisingly well. It's very difficult because a few years ago anyway, it took I think it was 1 day of computer time, or maybe it was 1 hour of computer time to get 1 year of Earth time. So to do a 10,000 year simulation, it took 10,000 hours of supercomputer time. All right? It's faster than that now. It's an order of magnitude faster, but I haven't found the most recent numbers. And that kind of thing's being done down in Cheyenne at the National Center for Atmospheric Research. What they're saying at their center now is that the post-processing takes longer than the model does. So they're making big improvements. So if you look at the International Panel of Climate Change Paleoclimate chapter, they will look at these things at this period right here when it's warmer, and at this one, and they will show the experimental data and compare it to their models. So they have 4 independent ways of measuring carbon dioxide from here all the way through. So there's very good information. One of those is from Wyoming, down in the Green River Basin. There's certain sodium carbonate minerals in the holite or something like that. I can't. Where's Ron? Oh,
He had to leave.
But one of them will only precipitate in the presence of in a body of water with sodium chloride. It will only precipitate when carbon dioxide in the atmosphere is above 1,000 parts per million. So we can get very good measurements of carbon dioxide, temperature. There's many independent ways of measuring temperature in this period. And so they're constantly doing, one of the journals is called Climates of the Past, and they're constantly trying to reconstruct all that. Generally not because they're talking about global warming, but they want to understand past ecology. What was the Earth like in the past? And sometimes in the past there were things like crocodiles up in the Arctic, like at the end of the Permian. This warm period right here, 6 degrees Celsius above what we have now. There were animals that have to live in the tropics were living at the Arctic Circle. If you look, I want to look at this part a little closer, the Phanerozoic, you'll see a big dip right here and an increase. Most people think this was caused by living things. So I wanted to point that out, that we're not the first living thing to alter the climate. And the evidence for that, this blue bar here means there was an ice age, recurring ice sheets like this. Like if you shortened the time scale on this, it would also be a big decline like that. If you look at the chemistry, carbon dioxide went down dramatically, oxygen went up dramatically, and that's the evidence from actions of plants. So plants suck all the carbon dioxide down, produce oxygen, and the temperature drops and they get an ice age. And it goes on for about 90 million years. And these are, it's kind of actually shocking how much carbon dioxide changes. This scale right here is how many times the current level. So this would be 20 times as amount of carbon dioxide in the atmosphere as we currently have. So like 8,000 parts per million. This part of the curve right here, I think is pretty suspect. There's not very much data on that. This part right here is very good. Yeah, independent means. So the amount of carbon dioxide in the atmosphere is fluctuating definitely from 10 times the current amount down to the current amount. And it's highly correlated with temperature. So
So if I look at that, and you say man's been around 2 to 3 million years, we've mostly been cold.
right. In fact, some people say this cooling here is what helped originate the human species. Two things went on here. Humans came into existence, but in Africa, the vegetation changed from, so that you had more of these grass, the
Yeah.
grass species exploded. A lot of the grass species originated then. They're fairly new plant family. So I think it's important to keep these climate change arguments in context. I mean, they might be very hard for humans as a part of their cities and their culture, their economy and all that. But as far as the Earth goes, the Earth has been going through huge changes its entire existence. I'm kind of surprised that argument's not used by some people. Here's the correlation. I brought this up because it's kind of a subtle thing going on here. This is the ice ages, so the scale here is 400,000 years to the present. Temperature anomaly, carbon dioxide. Now, so this is a ice age, warm period. Yeah, warm period, ice age. And the best thinking, like for example, what you see in the models, the physics models, is what's going on here is the amount of radiation coming off the sun changes because our orbit changes. The eccentricity of the orbit, the tilt of Earth's axis, and how we precess. When that temperature changes, it changes the solubility of carbon dioxide in the water. So you can have carbon dioxide come out of solution and it communicates, for example, let's see how the solar change that's affecting primarily the southern hemisphere, because sometimes they're out of phases. Some changes affect just one hemisphere. You have these gases come out of solution and they can communicate that change to the rest of the globe. So when you want to simulate an ice age, you have to put everything in there. You can do it. You can repeat these things in a model. Again, this one is Phanerozoic sea level curve. And the scale here, it's pretty dramatic. This is current level, 100 meters of increase, 200 meters of increase. So back here in that ice age in the Permian, you had 100-meter changes, or 200-meter changes in sea level. And so I put Florida and North Carolina, this is the Outer Banks, because many of us have been to these places. So on this scale, on the Outer Banks, the dark green is what would be go underwater if sea level went up 1 meter. And all of this is developed. I mean, all these barrier islands are jam-packed with houses. And that's just 1 meter. And if you count the surge from a hurricane, you can't just be happy with being, an inch above sea level. You have to be a ways above. And so if you're an insurance person, say you're a young insurance person, you have a career ahead of you, you have to think about this when you're making decisions for your company, right? I assume that these insurance companies have on-staff climate people because they could be wiped out. Or a banker that's trying to, should they write long-term mortgages for example, some building projects, if they're financed over 50 years, they're going to be going into these times. And so, like the way I like to think about the effects of climate change is property values. Okay, it's not the noble way to think about it, but it really brings it home. What's going to happen to the property values on the Outer Banks just over the next decade or two? Over here on Florida, okay, so this is the current. If the sea level went up 5 meters, these dark blue things would be submerged. If it went up 10 meters, the light blue would be submerged. And these numbers are interesting because if Greenland melts, That's roughly what would happen. And the prediction is that Greenland, over the course of roughly 1,000 years, will melt. And that evidence is from the past. That Greenland, and they can find these changes by looking at islands in the tropics. Where's the reef line? It's kind of complicated because you have to take into account tectonic changes. So it's a lot of work to do that, but they can see that Greenland has melted several times in the past. Antarctic, probably not. So these changes are things that a young person now is going to see probably in their lifetime. They're going to start to see this stuff happen. That's the end. Yeah, go ahead, Peter.
You guys have done an extremely good job, very competent job of summarizing climate as it's currently understood by most scientists. And I applaud that. And what I'm going to say has nothing to do with the science that you're reporting, or with your decisions about it. It turns out that there's a fundamental misunderstanding about what energy is, what thermal energy is. Climate models today, all the radiation codes used today, calculate that there's much more energy in the infrared than there is in the ultraviolet. But you and I all know that when you stand in the sun, you get sunburned and you get very hot. And when you stand outside at night in the infrared, you barely get hot at all. Atmospheric chemists and physicists know that energy is equal to frequency times a constant. And that means that the infrared is 48 times less energy than the ultraviolet.
Sure.
So, one of the things that was missing in the description was the stratosphere. The kinds of models that Mike started out with. The kinds of models Mike showed are exactly what a lot of people show. But the stratosphere, the top of the stratosphere is 70 degrees centigrade hotter than the bottom of the
Sure.
stratosphere.
What those Earth system models are doing, they're not using the simple model.
Okay, the
They're
stratosphere.
using all the levels. They have.
Well, I know those models inside out and backward.
Okay.
The stratosphere is heated by the sun, and it's heated by dissociation of oxygen and ozone primarily, also other gas species, NO2 and others, CO2, but it's heated by the sun. The stratosphere is an electric blanket. Electric because the energy comes from the sun, not from the body under the blanket. The existence of the stratosphere is the reason why Earth is 33 degrees warmer than you calculate.
Well,
And
what
the
I would-
radiative surface from the outside of the stratosphere is exactly what you calculate for that distance.
Well, I would say two things. First of all, that like all science, the way to test that is to make a numerical model and calculate it and compare with experiment. So to say it in words is to present an idea, but to convince somebody of that, no matter what field it's in, you have to go, here is my exact numerical prediction of how it works, and test it. The second point I'd like to make on the energy and the radiation, and Mike might want to add something to this, is that this idea of how radiation works is verified every day in millions of ways. For example, if you go into the hospital, most of the diagnostic procedures that you use are going to use radiation. Radio waves, infrared, X-rays, all the instruments, all the frequencies are used in that hospital. And that same theory that's going into this black body is what built those instruments, like that MRI. That MRI is a very sophisticated quantum mechanical device. The same if you went into the blood chemistry lab, they had an infrared spectrophotometer.
Well, which is more dangerous, X-rays or visible light?
Well,
Which is more energetic, X-rays or visible light?
well, the thing with that is not what one photon does, but the total effect.
Well, yeah,
Go ahead.
that was what I was going to comment on. Because, Peter, in your analysis, you're really discounting most of what's underneath the black body curves. But the Stefan-Boltzmann law is the integral of that. So all of those, you're right, there's more energy per photon in the ultraviolet. But there's a lot of area in the longer wavelengths.
It doesn't, when you say E equals H nu, energy equals frequency times
Right.
Planck's constant, bandwidth is not included. It is not a function of bandwidth.
But if
It is
you-
not a function of the number of photons. It is
Yes, it
simply
is the total
a
energy.
misunderstanding of what energy
It
is.
is a function of the
Well,
number.
all right, I think the way to settle that though is to look at the millions of experiments that are done every day in a
Do you
practical
realize
way.
that it's never been shown experimentally that if you take two containers of air and you put twice as much CO2 in one as the other, that the temperature actually increases? It's never been shown experimentally. It's only been tested once, and that was in 1900. So one of the things I've done in November, I issued a challenge worldwide, directly emailed to 2,000 of the scientists who wrote the IPCC report and to those who reviewed the IPCC report. I'm offering to pay $10,000 to the first scientist or even non-scientist who can demonstrate experimentally that doubling the CO2 content would actually increase the temperature of air.
Right, well,
But why is that important?
Because if it doesn't, then the whole greenhouse gas theory
No, you see,
doesn't
but
work.
that's based on your assumption that the cooler atmosphere cannot
No,
emit
it's not based
radiation.
on any, if you're saying that doubling the greenhouse gas theory is gonna, doubling the greenhouse gas content is gonna cause the world to warm somewhere between 2 to 5 degrees centigrade, then if you double the greenhouse gas content in a laboratory in a cylinder, you should see the temperature rise something like degrees centigrade.
Well, but
Well,
if you look at the tropospheric temperatures that were in some of that data, the tropospheric temperatures are going up. The atmosphere is getting warmer as well. I
the
mean,
be-
it
the
is.
best
It's measured.
experiment is the geologic experiments that you can see all across Wyoming and Utah, where we have data on the carbon dioxide, the temperature, and we have a model that connects the two. That's the way scientific evidence works. You have the model that predicts. And so let's say you have a model and it's making predictions and you have wide consensus on the agreement on that. To overturn that requires extraordinary support.
The models are wrong in the way they calculate energy, therefore, what
I
the
don't think
models
they
show
are.
don't matter.
I think they
I
are.
guess
Now,
we
wait a
need-
minute. I gave a talk 8 days ago at the American Meteorological Society meeting. The room was packed, and there were dozens of people there who were the top atmospheric chemists and other things. My talk was just before Mario Molina, who got the Nobel Prize for ozone. As a result of that discussion, as it led from that talk and the discussions that are ongoing with those people, I have a document about what the fact is that thermal energy is not additive. You can't add energy together like photons or even watts per square meter.
Well,
This is currently being discussed nationally by a number of leaders. I have copies here for anybody who would like to read it.
well, okay, I'd like to answer that first in 2 ways. One, being famous means nothing in science. It's actually correlated with making mistakes. So that's totally irrelevant.
I'm not sure what you're
Two,
referring to.
what's interesting about this, it's very economically important. It's going to affect, it's already affecting Wyoming. I mean, low natural gas prices are affecting it more, but it could affect it dramatically in the future. Everyone has a vested interest in this, so we have to be very careful. But let's go ahead.
Let's take two more
John.
questions. We're well past two, you
Sure.
guys,
Go
or
ahead.
one.
Could you talk a little bit about, you mentioned this briefly, that there is a correlation between historical temperatures going back 500 million years and CO2 levels.
Right.
Could you expand on that a little bit? I mean, is that, if you overlay those, do they pretty much overlap?
They do.
Yeah, they do.
And
It's
so what other factors would be driving it?
The things that really affect climate fundamentally are tectonics and life. Tectonics, because like we see a big tectonic effect right now in that Antarctic's right, the South Pole, and it's surrounded by that current. So there's always this source for the cold. It can provide stability to a cold regime, where Greenland doesn't provide stability because it's connected by current. So tectonics is fundamental to climate. That's the fundamental thing. Like if you bring up a certain kind of rock from the depths, you could draw down carbon dioxide through a chemical reaction. So that's the first thing to keep in mind. The second thing is life has a dramatic effect. Like our atmosphere is created by living things, oxygen. And so fundamentally, that's the two things to look at. And I think there's a pretty good, to me, the explanation is very good back to 4 billion years. Where it breaks down is the first couple 100 million years of Earth's history. There's still a lot of unknown about how it worked.
I'd like to also make a.
Hang on, right?
Okay,
behind.
okay.
Over here.
Let me ask you kind of a down-to-earth question here. I have a question about measuring temperatures, whether it's in the land or the air or the water, over long periods of time. Now, you can go back to the prehistoric time and measure from some indicator of temperature, not the actual temperature. But I'm concerned about measurements that are made, say, from 1850 forward, where you had some reasonably accurate instruments. And then what has happened in the meantime, say like from 1940 forward, where you're taking a measurement at some point, you've been taking it for decades, and all of a sudden that location is no longer viable for taking a measurement.
Well, that's why I said that sea level is the best thermometer. Looking at a mercury
What's the
thermometer
reference for sea
outside
level?
of Omaha is, well, sea level, recently in the last 10 years, we have satellite altimeter that follows the change. The other changes that we've had over the last 150 years are tide gauges. Now, tide gauges are tricky because you have the oscillation from the tides, of course, which you can remove with a Fourier transform, but the more complicated things, you have wind patterns, tectonic changes, but that is the key thermometer.
It's a mechanical system. You're dependent on a mechanical relationship.
Well, the satellite altimetry, you're shooting radiation down, microwave.
Yeah, but you're dependent on the satellite orbit and knowing precisely where that satellite
Sure.
is. And there are always errors in here, but we're talking about sea level changes that are in centimeters or
Right.
millimeters or
But,
whatever.
I mean, all you have to do is go look out at somebody's survey tool to see, that works.
The survey tool.
So
I'm
the
sorry, I'm
survey
an
tool,
engineer.
the survey tool can get down to
Yeah.
millimeters now. As we've heard people talk about in here up at Yellowstone.
Yeah, yeah, I
So,
mean, the
you
actual
know, they
level
think-
instruments have not changed since about 1860.
And, the thing to keep in mind, this is a very economic issue. And so what would the criterion be that you would use if you didn't care about the economics? Like if you're looking at Yellowstone's earthquake monitors, satellites work great.
Mike, you-
Yeah, I just wanted to make maybe a few concluding remarks. The point